In this video, we're going to talk about tail recursion. We're going to use the examples we've seen before, but now we're going to rewrite those methods so that they utilize tail recursion. Now, before we talk about tail recursion, I want to point out a drawback to a recursive method like this. So you'll notice that once it actually makes that recursive call, it's got to use that value in order to calculate the sum. So we add n to the result of this recursive call. Now, the downside here is that I make all these recursive calls and then I have to undo them each time, returning back whatever the result is so that I can reuse it. So as I make this recursive call, I'm waiting to get something back so that I can use that to actually calculate the result. So a more efficient way to do that would be with tail recursion. Now with tail recursion, what we're going to do is we're going to have an integer n the same as we had before, but we're also going to have an integer x. And this x is going to be the actual result so far. Now, the user doesn't need to know that we're using that, so let's create an overloaded method. And this overloaded method is just going to call sum up tail with n, and then we're going to start with 0 because the sum of nothing is 0. So now, if n is less than 1, I'm going to return x, because x is the sum up till that point. If n is less than 1, then there's nothing to add, so that's going to be our result. Now if n, and actually that should be it there and it there, my recursive case, I'm going to return sum up tail. So what I'm going to do is I'm going to add n to x, and then n I'm going to subtract 1 from. So essentially I'm starting with 0, and I'm going to add n to this total until n is 0. So this would be n plus n minus 1 plus n minus 2 and so forth. The thing to notice is that I just return the value of this call. I'm not doing additional work with it. So to get the solution, I don't ever actually have to revisit this function, and the compiler typically will be able to optimize that out to become efficient. So we talked about how sometimes recursion isn't efficient. Well, in this case, it will be, because there's no reason for the compiler to force this to go unroll the call stack. Once it gets to the end, it knows the solution. So now let's take our factorial and rewrite that in a tail recursive manner. So just like before, we're going to call a helper method, and then we're going to start at 1 this time because we're going to be using multiplication. Now here, if n is less than or equal to 1, we're going to return f, and then otherwise we're going to return fact tail n minus 1 f times n, and that gives us our result. It may seem confusing how this works because this isn't quite the clean mathematical definition we had here, but if you think about it, what this is saying is this is keeping track of n times f, and this is keeping track of taking 1 off of n. So each time we do this, this is originally going to be 1 times n, which is just n. Then the next time we're subtracting n minus 1, so it'll be n times n minus 1. Then in the next recursive call, we're subtracting 1 from that, so it's times n minus 2, and so on and so forth until we get to 1, at which point there's nothing left to do, and then we can just return whatever this parameter is at that point. So here's an example of what that looks like. If we do this non-tail recursively, So fact3 is going to call fact2, and it's going to rely on the result to calculate that end result. Fact2 is going to call fact1, and it's going to rely on that result to calculate fact2. And fact1 is just going to return 1 because that's our base case here. So we return 1, that gets used by fact2 in this multiplication, returns it to fact3. Fact3 uses that result to calculate 6, and it returns 6. Now if we do this tail recursively, notice fact-tail helper is not waiting on the result here. It's just going to return whatever that call is. Same thing here, fact helper of 2, 3. It's not going to care what's there. It's just going to multiply 2 times 3, subtract 1 from n, and then return whatever that result is. So when I get to this last base case, I know what the result is. I return to here and here and here. And so the compiler, again, can do some optimizations there. So that's an example of tail recursion. Again, which one is better? Well, typically tail recursion is going to be preferred because it can be optimized by the compiler a lot easier, although sometimes the code for Factorial is much simpler. You can think about some of the other recursive examples we'll see this semester, and think about if you tried to make those iterative, it would be incredibly difficult. So let's add some calls to these methods just to make sure that they do work. So pretty much these are all going to be the same as the non-tail recursive. We just call the tail recursive version. So I can copy and paste this, and then do the same thing for Factorial. Copy and paste the existing one. And let's run that just to be sure that it works. And it looks like the results are the same each time. That's what we would expect. But again, if you'll remember, we talked about, since these are tail recursive, now the compiler can optimize those so that we get a little bit of an efficiency boost.